I did start recording, just so everyone's aware. Okay, everybody, I'm missing 2 data collectors. Whoever has the gray one, I need that one. Yep. I do want to charge these. Do you know which one was yours?
Yeah. Those are gray ones.
The gray one? Gray one's out and about somewhere. Everybody has their points loaded, feel comfortable. Did the batteries die on anybody? I'm going to charge them up tonight, so there shouldn't be a problem. They don't use as much power as the instrument, which I find opposite. I would think they would use more person.
We didn't put our tin yet, but I barely punch it. He's over it. He wrote it.
Can you guys show up a little early tomorrow?
Yeah, we do.
I'd feel better if I just put it on charge. Because, I mean, that one is the oldest. Believe it or not, this is probably 30 years old. So. I want you guys to do it now. Because I'm recording this, so you guys can.
We just don't have the suited civil group.
Oh, okay.
That's the thing.
All right, yeah, just.
We'll do it.
Okay. So what I wanted to start going over is some of the stuff that I had you guys working on in Civil 3D. You have to know sort of the background of how to do all this stuff manually. Okay, what is the software doing? So we went over how to calculate azimuths, right? We went over how to calculate coordinates from azimuths and distances. It's basically applied trigonometry, right? It's knowing sines, cosines, and creating x's and y's from sines and cosines, and creating interior angles from azimuths and vice versa. So that could have been an example of your traverse, right? On the test, what I'm going to ask you to do is I'm going to ask you to balance a traverse. There's multiple ways to do it, okay? The most common and simple way is what? We already kind of talked about it. I didn't make you do it, but we talked about it. What's that? Yeah, you can plunge the scope. That's going to take the error out of the instrument, or at the very least half the error in the instrument. So how did you figure out your angular closure?
What's a mathematical
Right, the sum of the interior angles, right? You just add all that up and you see how far off from what you're supposed to be. Right? So what could you do?
Correct the angle.
I'm sorry?
Correct the angle.
Correct it, right? And just distribute it over the number of setups that you have, right? Just say that the error is probably the same at each spot. And if there's 5 setups, I'm going to take my angular misclosure, divide it by 5, and apply it across the board. Right? their angular closure is 11 seconds total. So what they did was they just picked one and said 2, 2, 3, 2, 2 to make it add up, right? Because it's easier to work in even seconds than 2.2, 2.2, 2.2, 2.2. Okay. There's two other ways that you can do this. I'm just going to talk about these for the sake of completeness. You're not going to get tested on them. Okay. Can you think of another one or two ways to apply the angular differences that you could get? Any thoughts? I know it. What if you know that you set up on a spot where it was out in the woods and it was really soft ground, really muddy? You could probably say that the setup really wasn't so hot. I could sort of double the error at that spot. Right? That's one thing that you could do. Another thing you could do is you can prorate it based on distances. Right? So you can say the total length of my traverse was 1,000 feet. But this length here was 500. It was half of my overall, and prorated based on lengths of lines. Do you need to do that? No. As you all heard me use the term least squares, right? Yes, no, or am I? Okay. Has anybody else heard the term least squares outside this class? Okay, so you mind telling me where you heard it?
Competition that it's cost.
Yeah.
To like solve with a matrix.
Yeah, that's exactly what it's for. Let me see your hand up. Did you see least squares before? In statistics, yep. So you're dealing with matrices, you're dealing with multiple equations. We're not going to get into a least squares adjustment here, but that's sort of what's running in the back. Most people in industry that do least squares of adjustments on traverses, they're not doing it manually, they're doing it with software. Okay. Most people don't even know how to do it manually. And I'm not going to get into it in this class. Maybe if you were doing a 4-year surveying degree, you would get it, but not. Okay. Just recognize that that's what's going on in the background of a least squares. You're looking at your interior angles, you're looking at your lengths of your lines, and it's prorating it based on that. Okay. But for the sake of what you're going to do, divide the area, and then you're going to balance your traverse. So if this is your measured angle, your total angle that you're off is 11 seconds, successive differences, and then you're going to adjust it. But you need to know which way to adjust it, right? You're over. So if you're over, what do? Subtract. If you're under, what do? Okay, not rocket science, right? Okay. Computations of azimuths, we've done that. Latitudes and departures, we've done this. Departures delta x, latitudes delta y. Angle is your azimuth. If you want to use delta y, but this angle, then you'd be using sine. Right? Everybody see that if you're using your azimuth angle, it's cosine. Everyone sees that? Opposite adjacent. Okay. So that's sort of what's running in the background. One thing that I do want to make note of. Good, everybody's here. I don't have a slide for this. And I'm not gonna write everything down on the board. Everybody has a copy of the textbook, yeah? Something that is going to be on the test. Chapter 9, the very end of it. It goes over sources of error in traversing and mistakes in traversing. Read that, understand it, reflect. Think, act, reflect. Everybody remember that? So when I say reflect, think about your traverse. Oh, man, that makes sense. That's maybe some of what happened. Okay. All right. I'm going to close this. So when we located the benchmark that was Colton's spot, you couldn't physically locate it distance-wise, right? So we came up with two lines. Well, we've done it in the computer. What are some mathematical trigonometric things that you've learned in your career, right, that you could use to solve this? So you've got a triangle, it could be any triangle, right? So it's not a right triangle, so we're not going to go that far back to the trig. Everybody remember? Somebody said it. Start off with law of sine. Do I need to go through this, or are we pretty good with this? Okay, some enthusiasm. So I don't need to go through this? Or do it as a review?
I think,
Do it as a review?
I'm gonna say just at least write out.
Write them out? Okay. Sine A. So everybody follow that this is angle A. This is angle C. This is angle B. This is AB, or length AB, length AC, length BC, or length CB. Everyone good with this? Everyone okay to apply it? Okay. So what goes along with law of sine? Law of cosine. Law of cosines is a little bit more long in the tooth, but it's the same kind of concept. You'll have one or two of the angles and one or two of the sides. I'm sorry. Law of sines, you have two angles and two sides. Law of cosines, you have two sides and one angle, right? C squared. B squared minus 2 AC B. Okay. AC squared BA squared. That's a pretty horrible. A squared 2 BA BC C. And then a B squared. So this is all kind of what's running in the back. Right? Yes. Did I mess something up?
I just don't know. Two of them have cosine A and I just don't.
You're right. Thank you. What are you allowed to have on the test? Equation sheet. What are they? All right. Who remembers this? Oh my God. I'm an engineer. I don't need to know that, do I? Yes. When I teach calc-based physics, kids get ticked off. I gotta know that. No. Yes. Do you need to memorize it? No, I need to write it down. My whole take on math is you don't have to memorize the equations. You have to know how to use them. That's more important, right? Every time I need to know quadratic equations, quadratic, there it is. Okay. Let's talk a little bit about simple lines. Everybody done writing? Okay. Simple line, right? Point A, point B, and any point on the line in between, we're going to call point B. It has coordinates X and Y, X and Y at A, B, D. Why is this picture misleading about M and what is M? Anybody remember? What does M represent? Just somebody said it. Slope, right? What is slope? Rise over run. Why is that misleading about slope? Because it looks like it's just the rise, right? It's meant to represent rise over run. So everybody recognizes at least that part of it, which is awesome. I don't need to keep this, right? We're all good. So I'm not going to redraw that, okay? Everyone's okay if I don't redraw that. So if I want to know the length of AB, just the length of it, how do I figure it out? The right triangle, right? Joy. Pythagoras and his buddies, right? A squared plus B squared equals C squared. It's just solving it for one thing, right? So what Joy said exactly, delta X squared plus delta Y squared. Does it matter if I do delta Y squared plus delta X squared? No, it's the same thing, right? Agreed? Well, what is delta x? It's just the x coordinate at B minus the x coordinate at A plus the y coordinate at B minus the y coordinate at A squared. Right? So that's the length of A to B. It could also be A to P or anything in between, right? Well, that's handy. What other things can we glean from this? Take note that this figure is using what? Azimuth angle, not this angle here. You have all had plenty of math to figure out what that angle is, right? Might need a little work on the degrees, minutes, seconds part of it, but okay. You can all just take 90 and minus the azimuth and do it that way. Right? But I do want the whole board. Can I erase this? So if you have length AB, rewind. If you have azimuth AB, azimuth AB is the inverse function of tangent delta x over delta y. Everyone's following delta x. Why it's delta x over delta y, not delta y over delta x, because it's the azimuth. If you wanted to do it the other way, you can. You just got to get a different angle, and then you can do delta y over delta x. Did I go too quick there? The reason the book does it this way is because they put this little plus c on the end. It's not quite like calculus because they tell us that c is 0 degrees if delta x and delta y are positive. So there's no adjustment needed at all if your x's and y's are positive, because you're in that first quadrant. All right. What if you're in one of the other quadrants? So if C is going to be 360 degrees if both delta x and delta y are negative. So you're going to add 360 degrees to it. If delta x and delta y are negative. Everybody follow why? You're going to be up in that quadrant. Yeah. So if x and y are both negative, quadrant one. There's only one spot where both delta x and delta y are negative, right? Just down here. So what you're doing is this is 0 and 360. So you're getting the azimuth backwards from 360.
Oh, it would be.
Right? Because the number is going to be negative.
Oh, got it.
Sorry. So because the number is going to be negative, the 360 gets you to a positive azimuth. Does that clear that up? C is going to be 180 degrees if your delta y is negative, but your delta x is positive. And this is all meant to get you just a positive number. Right? That's the only thing driving. So if you've got a picture and you can sort out the math in your head, you can just use conventional sines and cosines, if that's easier. Does that make sense? This is also in the text. Right? Yes. I'm sorry, can you repeat that? No. No. If delta x and delta y are both positive, there's no adjustment needed. If delta x and delta y are negative, then it's 360. So then we've only got one other coordinate to worry about. That's where delta y is negative and delta x is positive. Right?
I think what it means is that delta x is negative, delta y is positive. Which one would you use? If it's still 180.
Yeah.
Okay.
Sorry. Yes. Okay. We good? Okay. Can I erase it? Can I not erase it? Yes.
If x is negative and y is positive, would it be the same as the bottom one?
We good? What is the other most common expression for a line? Mathematical expression. Joy. Sorry? Yes. Yep. Exactly. Y is equal to mx plus b. Right. What is b? Y-intercept. Right. What is m? Slope. So m slope rise over run, or delta y over delta x. Does everybody understand that in civil you are going to be using slope a lot? Pipe slopes, whether they be, it doesn't matter what kind of pipe it is. If it is a gravity pipe, you are always calculating the slope. But in surveying and on civil plans, they report it as a percentage of 100. Right? So a 1% pipe, right, 0.01 is a 1% pipe. Pipe is laid at 1 foot in 100 feet. So it only drops a foot in 100 feet. Is that enough for most types of pipe? What do you think? Yeah, it's enough. When you get into sewer design, at some point along the way, you'll hear the term self-cleansing velocity. That's the velocity at which that if there's something in the pipe, that any liquid that runs through it, which is going to be water, is going to flush it and keep it moving downstream. If it's a storm pipe, should there be anything in there? There shouldn't be, but the reality is there's plastic bottles and junk and rocks and road debris and all sorts of nasty stuff that flows through those pipes. Usually the minimum pipe slope that you'll see is on a sanitary sewer line. And that's usually 0.5%. So it's a 1/2 foot under. Pipe crews don't like it, but they can lay a pipe that far accurately. You have to get a laser out of the which usually don't like doing that. Anybody know the maximum length you can have between a manhole? You know what I mean by a manhole? Everybody ever see the circular metal rings in the middle of the road? Well, what you see on that ring, that's called the riser section. That's called the riser section. Anybody want to take a guess at what the cone section is? That's the cone section. This is usually called the riser or chimney. Again, obvious, right? And this is the manhole. So the part that you see up here is usually about 18 inches in diameter. This thing opens up and it's usually 4 foot on the inside. And there's usually ladder rungs that are cast into this that you can climb down in there if you had to. You don't really want to, but if you had to, you could access it. And then at the bottom of this, when you look down at it at the top, okay, you have a pipe coming in and a pipe going out. There's usually a concrete channel that's poured in here to kind of force it to go where you want it to go. Most of the time when you open this, you just look down and see if there's an obstruction. If you open it up and it's full of liquid, what do you know? There's an obstruction somewhere downstream. Okay, so you keep working your way down until you find where it is. Okay. The other thing, sometimes on the tops of these, if they're in a floodplain next to a stream, they'll have, it's like a plastic bowl that fits down in the top of this, like a molded plastic piece. Anybody know what that's for? Next to a creek or a stream, have you had any discussions in environmental class about I&I? Anybody heard of I&I? Inflow and infiltration. When water goes through the system, have you guys toured the sewer plant yet? Okay, so every bit of water that goes through there has to be treated, right? So rainwater, groundwater, do you want to treat stuff you don't really need to treat? No, right? You want to keep inflow and infiltration to a minimum inside the system. So is that the best way to do it? You're going to eliminate some. You're not going to eliminate a lot, but you'll eliminate some. Okay, so back to slope, rise over run. Okay. So for the purposes of what we're doing, delta y over delta x, y at point B minus y at point A, x at point B minus x at point A. Or would that also not be equal to the cotangent of the azimuth AB? Why cotangent? This is this, right? So now, in surveying in these data collectors, you have coordinate geometry, COGO, for sure. a lot of times it's important that you do line intersects or direction intersects. It's the same thing, right? We have two line segments that intersect. You could have a line arc intersect. How many solutions are there for a line intersection? There's one. How many solutions are there for a line arc intersection? Two. How many solutions are there for an arc or a circle intersection? Also two. So you need to know what solution is getting reported back to you. We're not going to do arc or line arc intersections. We're going to work mainly with line. A lot of times it's also helpful to know a perpendicular distance. Right? So let's say that you wanted to go this way, but there's a tree in the way. So you had to set an offset point. So sometimes it's helpful to create a point that's at 90 degrees. But everybody kind of see that what is this? It's just a line intersection. Right? So where are we going with this? We're not going to get there today. I'm going to draw this once today. Can I erase? Yeah, so slope on line segments is something that's going to revisit you lots of times. Right? So in this class, near the end of the semester and in transportation, you're going to look at something called vertical curves. It's a bit of a nomenclature error. Does anybody know what a vertical curve is? Okay. Yeah, so like when you drive down the road, if there's a grade break, either uphill or downhill, does the road actually do that? Or is it like smooth? It should always be smooth. Right? A vertical curve is not actually a curve, it's a parabola. That's why it's sort of a naming here. So you can have a horizontal curve and a vertical curve. Vertical curves, the percentages are slopes, because you need to know the slope in and the slope out. More on that later. Just recognize that slopes are going to be with you for a while. Okay. So this sketch is also in the textbook, right? I'm going to draw it once today, but I'm not going to redraw this on Wednesday. Fair? Okay. So you have your X and Y coordinate system, kind of like in CAD. Got a point here. So I'm going to call this A. I'm going to call this B. And I'm going to call this E. And I'm going to have an instrument set up here. I'm going to have an instrument set up here. And I'm going to locate it with the rock. But actually, let's just say this is the spire of the chapel, because we can't get a distance for whatever reason. Okay? All we can get is a direction. Now, for each one of these, I'm going to have my azimuth A to P, right, which is measured from vertical, right, or north. Everyone follow that? Is that the same as interior angle A? Ooh, two different things. Just be careful with that. Up here, I also have azimuth, but this azimuth is B to P. Okay. And I also have angle B. What's that at? So at point A, right, I have X at A, and I have Y at A. I have, for point B, I have X at B, I have Y at B, for point B. And same thing for P. I have an X coordinate, Y. P. Angle A. P. Everyone good so far? Okay. So now, if I want to know angle A, right? Angle A is going to be the azimuth from A to P minus the azimuth A to B. Everyone follow that?
Because A and B is bigger. Or is it an absolute value?
Because it-
No, it's AP minus AB. Because what I'm doing is I'm getting this azimuth here, right? Minus this azimuth. So AP is this line, right? It's not AB. Or I'm sorry, it's not BP.
Okay, yeah, that's.
It's not BP. It's A to P and A to B. So that's good?
Yeah.
So then angle B would be your azimuth B to A minus your azimuth B to P. Everyone see that one? Visualize that? Now for angle P, you could do the same thing. You could do azimuths, or what else could you do?
Trying the other angles.
180 minus angle A minus angle B. Everyone with me so far? Omar, what do you got? I'm sorry, can you repeat that?
I can't realize how getting the difference between the azimuth angle and zero angle over time.
Okay. We're looking at this point here, point A. This is point A. Everything azimuth line is measured from north. Agreed? You good with that part? Okay. So I've got two lines going out. We're going to call this AP, and we're going to call this AB. We're good with that? Okay. So if I want to know this angle here, which we're going to call angle A, right? If I take A to P, if I take this angle here, from here to here, so this is azimuth A to P. With me so far?
Yeah. Very cool.
And this is azimuth AB. This is from here to here. This is from here to here. Right? So if I added angle A plus azimuth A to B, it would be azimuth A to B. You see that? So now do you see how this is the difference between this? So it'd be this minus this to get to this. Did that help?
Definitely.
Everyone good with that? Anybody not good? So now we had our azimuths A to B and A to P, right? We got that from the total station. Right? So now, if we go back to law of sine, length from A to P is going to be equal to the length AB sine of angle B divided by sine of angle P. Right? This is just going back in and plugging things in into law of sines. You could do law of cosines too. Actually, could you do law of cosines? No, because law of cosines, you need two what? Two distances. Law of sines, you need two angles, right? What was that?
Choose both for all sides, but you have two distances with two sides. It's just-
You could, but so let me ask you another question. You're looking for the coordinates at X or Y. Or you're looking for the coordinates of X and Y at point P. You have two unknowns, right? The X position and the Y position. How many equations do you need? Just two. What two equations you used? Could you do this with the slope equation? Sure. Sure, you can get the slopes of A to P and A to B. You know, that's one way to do it. So we're going to pick this back up next time.